All right, we're starting on chapter 9, and chapter 9 is about external flows over bodies. Chapter 8 was basically pipe flow, internal flow. In that case, in chapter 8, we're largely interested in the fluid, but here we're really interested in the fluid and the body because, well, this is a really important application area for fluid dynamics. Flow over cars, flow over airplanes, flow over submarines, flow over bicyclists. We had a graduate student a few semesters ago who got paid by a sunglasses company to figure out relation of flow to their sunglasses. Their sunglasses were used by high performance track athletes. So we are eventually going to do more complicated bodies, but to get for a feel for the type of questions, we'll start with the simplest case today. And then do a little bit more and then come back to this and get detailed. So this is basically a flat plate, and this is some fluid that's approaching it. U would indicate that it's horizontal, and this subscript here is not used in your ME120 book, but is oftentimes used in fluids, U sub infinity. That means fluid that is way far from any other bodies. So as a consequence, its flow can be uniform. There is no slip condition affecting things. There's no interference. So basically, this might be a case where we have some sort of plate like this and the fluid's coming across like this. It comes and splits with some going above, some going below. When would you practically have this? Well, actually, if you have a building where this is one wall here and we have a wall here like this and this is the roof, an important question with a building is under high speed conditions, what are the forces like here above that surface? So this problem right here, half of it at least would have some very, very practical applications. Okay, so what I'd like you to do is just pause the video and think for just a second, hey, what's that flow gonna look like over this plate once this fluid actually reaches it and goes past it and comes around here like this? At a minimum, think about the no slip condition. While you guys are pausing and thinking about it, I'll get the drawing up there and we'll discuss what it would look like and then what sort of analysis we need to do. All right, well, there's a lot that goes into it, but if you were to get one thing from this start, is that we want to be able to visualize and understand what's called the boundary layer. And the boundary layer in this case is this shape I created here like this, that's a dot that has a dashed outline. The boundary layer is going to vary a lot depending on the geometry, the nature of the fluid, etc. But regardless, if we are doing external flow, we want to think about the boundary layer. Okay, so a rough definition of what the boundary layer. The boundary layer is the area where this fluid flow, let's call it 20 feet per second, is affected. So if I were to go to one point like this and say to myself, hey, should that point be within the boundary layer? Well, the answer is because of the no slip condition in shear, the answer is yes. The fluid right here near the plate can't be moving. This fluid above here is probably generally moving to the right, but it is slowed down by viscosity and the relationship or the attraction to this little bit of fluid below that. So that in that area right there that I just pointed to, the fluid is actually going to be slowed down. Well, it's possible that everywhere in this region it's slowed down. In this upstream region, the fact that this plate maybe has even just a little bit of thickness might push back on the fluid and create some effect. Above here, it'll be slowed down because of the no slip condition in shear. Down below, it'll be slowed down because of the no slip condition in shear. In addition, there is going to be a wake region, which is the region beyond where there'll be some sort of effect. And what you can do maybe to help with that is imagine that you have some bit of fluid that's not affected, and it's going to come up here above this region, and then it's going to come back down here like this, and eventually follow its original path. More on that later. Okay, so one thing we want to be able to do is visualize the boundary layer, and the boundary layer is where the important stuff happens regarding external flows over bodies. All right, some other questions that we want to ask then as we're analyzing the flow in this boundary layer region. Okay, first of all, we're going to do a Reynolds number calculation. That's pretty standard for any sort of fluid. Secondly, we're going to ask whether the flow is turbulent or laminar, and that's an important question. Okay. Another thing we're going to ask is, what about the distance above the plate or the distance above whatever body we're talking about? An airplane wing, a submarine surface, the roof of some sort of building. What is this distance between the surface of the body and the point where the fluid is no longer slowed down or affected by the combination of the no-slip condition and shear forces? What is that boundary layer distance? Okay, then we'll get down to what it is that allows us to do good design. Okay, what are the pressure forces on this plate? Okay, or this body? In this case, it's pretty easy because remember, pressure is always into a body. So right there, the pressure force will be there like that. Okay, what are the shear forces or the shear stress? Well, remember, okay, this plate right here is slowing the fluid down. Okay, and so then as a consequence, there will be a shear that's horizontal, and we'll get into that later on. Okay, are there any lift forces? And are there any drag forces, and how do you work that out? So, pretty extensive order of business. Let's get a little bit more understanding of these ideas on the forces over there, and then we'll get back to the flat plate and work out some of the numbers. So some conventions that are used when we're analyzing external flow. Okay, this crude drawing is supposed to represent an airplane, and we need to think about how we're going to represent flow speed, direction, and things like that. So in ME120, for the most part, we're going to do one-dimensional flow. Okay, and in this case, we could be thinking about drag and lift in a variety of situations. One situation where this plane could be moving 500 miles per hour and the surrounding air could be stationary. Okay. Another case, we could put this in a wind tunnel that has 500 miles per hour going this way. The plane would be stationary. Finally, you could have the plane going, say, 250 miles per hour into a headwind of 250 miles per hour. All those are equivalent. And it turns out that what we're going to do, regardless of the situation, is we're going to make it into an equivalent situation where we fix the coordinate system with the body. So in a case like this, we would actually say, we're going to actually, in this case here, maybe put an x-axis going like this to the right, and a y-axis being vertical like that. And we're going to think of the plane's position as being stationary, and we're going to think of there being a uniform flow coming over this way here like that, like, well, whatever the speed is, 500 miles per hour, 800 miles per hour, 200 miles per hour, 30 feet per second, etc. Okay, so again, some conventions that you're going to see, every single drawing, the object's going to be stationary, and the fluid's going to be moving with some sort of upstream velocity, which your text calls u. Hang on for a second, got the lawn. All right, sorry about that. And so again, we're going to fix our coordinate system, and we have an upstream flow. Of course, this could be equivalent to this flow being stationary and this plane moving this way with speed u. Okay, and then again, we get to our questions. What is the boundary layer around this plane going to look like? If we went to any x coordinate along this plane, so for example, if we went to this wing point right here like this, okay, what actually is the pressure at that point? What is the shear at that point? Finally, we want to get to totals, of course, because that helps us with design. What is the total drag in pounds or newtons? And what is the total shear in newtons? All right, so your text does a really good job at getting to this conceptual side of things. And I'll ask you guys to look at some diagrams for homework number 9. Sample diagram. This is supposed to be a somewhat strangely shaped wing or foil. It might be called airfoil, and this is air flowing around it. And oftentimes we start by going point by point and thinking about pressure and shear. So we're going to start with this point right here, okay? And we're going to think about pressure and then lead from that, go to drag and lift. So what I would love for you to do is pause the video at this point and think, okay, what is the air pressure right there like that? So do that shot. I'll draw it in a second myself. Okay, so pressure is always normal to a surface. So the pressure would be at that angle like that. Okay, now what we would say, trying to get a little bit more intuitive, hey, does that pressure right there, does that lead to drag, or does that actually create no drag at all? Well, if you take a look at this pressure, you can see that this pressure, if this plane were moving this way like this pressure would have a component that would be horizontal. So to analyze that, what you would do is maybe take that pressure vector and be a little bit patient with me, because I'm not going to be exactly um, uh, parallel to this one right here, are the same size, but you're going to take that pressure and actually break that down into components. There'll be a component of the pressure that'll be like that, and there'll be a component of the pressure that'll be like that. Okay, what does that component do? That contributes to drag. So if we can figure out the magnitude of this pressure and break it into vectors, component vectors, horizontal and vertical, we got the drag. What does this component do? Obviously that creates lift. So we've got drag and lift from pressure. But it's more complicated than that. If we're trying to get drag and we're trying to get lift, there's also shear. So let's take a look at that. Okay, well, hopefully your intuitions are pretty good. Going back to this main point here, or this point that we were concentrating on, okay, the shear of the fluid on the plane wing at this point is going that way. But just maybe a reminder to break it down just a little bit. If this represented a surface and there was a fluid below on that surface, okay, basically what we have is we have a force. If this is the body, we have a force of the body on the fluid that way. Okay, what's going on? Ordinarily, this fluid would move nice and easily, but because of viscosity, this body ends up slowing it down. So the body is creating a force on the fluid that way. And then conversely, by Newton's third law, there would be a force of the fluid on the body to the right. Okay, and hopefully you can just even get away from thinking about viscosity and just being basic. Hey, if there's a fluid going here like that, it's going to tend to push that body there because there's some sort of interaction between the fluid. Okay, so how about here? The shear is going to push the body, the wing, back like that. It's kind of be a backward force. Gonna kind of be a backward force. Well, I don't sound like an engineer very much, so let's actually be more precise. Let's get the shear in there like that, and maybe pause it and see if you can break it, get the shear direction, and also go ahead and get the lift and drag. Okay, so there's the shear direction, and their book is going to use the symbol tau sub W, where W stands for wall. So there's shear at the wall of the fluid on the wall. Okay, does that contribute to lift or drag? Well, the answer is both, okay? Drag is backwards, okay, and lift is upward. So taking a look at it again, we're going to take this shear component and break it down into the shear force and break it down into two components. All right, this component right here, that's drag, and that makes sense. Fluids create drag as it moves along. This component right here, in a sense, is lift, but it's downward, so it actually counteracts the lift. So if we're going to get the drag, we have to add the pressure drag and the shear drag. If we have to get the lift, we have to take the difference between the pressure lift and this shear lift downwards. Wow, that sounds pretty complicated. So what we're going to do is start with a simple geometric situation of a flat plate. All right, well, I'm going to have a basic drawing where I'm going to try to get the fundamental relationships we need down. And here's our basic drawing. Again, we have some sort of uniform fluid at uniform velocity. All those arrows are supposed to be the same length. They are unaffected by the plate at this point. Here's the plate over here. We're going to make our x-axis go right through the middle of the plate, and our y-axis is going to be obviously be perpendicular. And let's see if you can just think your way through it really quickly. These four things. Is pressure going to contribute to drag or lift? Is shear going to contribute to drag or lift? Give you guys a second to think about it. If we were in class, we would pause and ask you guys to think your way through it. All right, well, pressure, okay? let's take a look at what pressure of this fluid. There is fluid up here like this, okay, but pressure is always normal to the surface. So this pressure is going to be in here like this, okay? That has no horizontal component, so there's going to be no drag associated with the pressure. What about lift? Well, lift in a sense could be down. If lift is negative, we call it down force. So this would create a down force, and up the corresponding over here would create an up force. If this were a building, we would actually be thinking about the down force there and be working our way through it. Fortunately, with this flat plate situation, these two are going to be balanced. It's perfectly symmetrical, and as a consequence, we're not going to worry about lift. Okay, what about shear? What about shear? Okay, again, this plate is slowing that fluid down, okay? And so as a consequence, there is going to be shear of the fluid on the plate that way, okay? Shear that way. And that is essentially going to be a drag force. So if you thought about it in a different way, remember this picture is equivalent to this plate somehow going to the right here like this and cutting through the fluid would create a drag like that. So yes, there is going to be a drag. We want to work that out. Is the shear going to create lift? All of it is parallel to the axis, so no, it's not going to create lift. And that's our first sort of background idea on the plate. All right, second set of conceptual ideas are about the boundary layer thickness and the Reynolds number. So let's start with boundary layer thickness. That would be at any point X, how high is the region where the fluid is affected by the presence of the plate? I mean, obviously, if this were the top of a building, okay, and we had a day with a 30-mile-per-hour wind, if you went 40 feet above the building surface, way high above the building surface, that wind is going to be 40 miles per hour here. And as I go down, 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 it's still going to be 40 miles per hour. But when we get closer to that surface, there'll be a region where the wind is slowed down by viscous effects. So that is the boundary layer thickness. And how does it vary as you go further down the plate? Okay, I'll ask you to look at the book in a little bit more detail for this, but really the idea is if you could think about some fluid marching along here, going from the beginning to like a foot in, then 2 feet in, then 3 feet in. Well, when it first hits this plate, okay, that's where it first encounters that no slip condition. And this little bit of fluid here is slowed down. Then as you go further down the plate, the fact that this bit of fluid is slowed down creates an effect on the fluid above it. So more fluid actually ends up getting slowed down. And as you get further down the plate, you get more and more fluid that's slowed down. And so as a consequence, excuse my writing, the boundary layer thickness increases with X. Sorry about my writing, but the boundary layer thickness increases with X. Okay, what about the Reynolds number? I haven't given you the formula for the Reynolds number, but remember the Reynolds number is first of all giving us an idea about what the likelihood of turbulence is at any location, okay, or for a situation. And secondly, it's giving us a ratio of the effect of inertia or separation forces to viscosity. And once again, it's really the same idea here, is that the more fluid actually ends up getting slowed down, the more divergence is necessary for the fluid that's coming along here like this. This fluid over here has to get over just a little bit, whereas this fluid, as it goes further down, has to deviate over this region, which is getting thicker and thicker and thicker. So as a consequence, we get more of a deviation the further down we go. Please don't stress about that too much, but at least copy down the idea that the Reynolds number is increasing with X. All right, and so that is our second conceptual idea for this set. And let's get the third one up there. How about the wall shear? Okay, what does that actually do with X? Okay, and all I'd like to do for now is remind you about how we figure out wall shear. What we do is we take the viscosity and we multiply it by the rate at which the velocity is changing perpendicular to the surface. So there is our basic equation from the first day of ME120, put in slightly different form. Okay, well, basically what happens actually is if you think about right at the beginning, the speed here is 0. And then if you go, because the boundary layer thickness is not very big, the speed here is much larger. So at the beginning, we get a large du dy, and we get a lot of shear. As you go further and further on, the rate at which the speed has to increase with verticality in order to go from 0 at this point to full speed at this point, that becomes less. And so shear decreases. I wouldn't expect you to memorize that as a fact. The most important thing is just the reminder that that's how we calculate shear in this physical situation. All right, getting down to equations. Please don't write this equation down, but we are responsible for some conceptual stuff and some equation stuff. So reminder, for fluid flow and interaction with bodies, pipes, ducts, bicyclists, parachutists, cars, skis, etc. It's been very successful to say, look, we're going to calculate a Reynolds number, which is going to give us a feel for the likelihood of turbulence of flow relationship to that body. And in general, the Reynolds number has this form. We consider the density, the fluid speed, some sort of length, and we divide it by the viscosity. All right, what is the length that's in this case? Well, this is even though this geometry is very simple, we add a little bit of complication that we speak of the Reynolds number at X, where X is the distance from the leading edge of the plate. X is this distance right here. So like if this were 2 feet down from the beginning of the plate, we would be figuring out RE sub 2, the Reynolds number at 2. Okay, so there is your first equation that you're responsible for. Remember, we can take this density and move it down into the denominator, and we can get a ratio of viscosity to density, which is called the kinematic viscosity, and that's worth writing down. Pardon me, I'm being a little slow here. Okay, so this is almost what you should write down. Of course, you should note that this is for flow over a flat plate. V was the term that we used for speed in the past, but in this case, your textbook, in almost all textbooks, are replacing speed with a capital U for the free stream velocity, and here is the other version. All right, let's get to work. What is the Reynolds number going to be like in this, where we have air flowing over, say, the top of a roof at 22 feet per second? That's 15 miles per hour. And what if we're 2 feet from the initial point on that roof? What is the Reynolds number going to be at that point right there, 2 feet in from the leading edge of the roof? We'll go. I'll work it out and we'll see what you guys get. All right, well, I got laminar. Whoa, maybe that takes a little bit of explanation. Well, first of all, for the Reynolds number, I got a huge number, 280,000 basically. These last couple digits don't matter all that much when you get numbers these large. So I took the U and I multiplied by the X, and then I did it using this version here because it's less work. So I did the kinematic viscosity. If you take a look, it works out nicely. The units work out, and we get a very, very large number. Okay, first of all, how did I come up with the idea of turbulent? Well, if you remember when we did pipe flow, there was a values where it was laminar, values where the flow was transitional, and values where the flow was actually turbulent. And we know those numbers for pipes, but I haven't given you those numbers for this flat plate situation. Okay, if you think about it, the value of the Reynolds number, we can make sense of it the following way. The value of the Reynolds number, which would lead to turbulent flow, well, should it be large or small in this case? Turbulence is created by the fact that we have a lot of no-slip surfaces through which our surface, or by which our surface needs to pass. Well, our fluid needs to pass. Well, this fluid's only encountering this no-slip condition down below. It's not encountering any no-slip condition over here. So it's going to take a relatively large Reynolds number compared to a pipe to get turbulence. Okay, so the critical Reynolds number, the Reynolds number where we say, hey, below it, it's laminar, and above it, it's turbulent. It varies with the smoothness of the surface, but for right now, for the most part, we're going to use 500,000. Every now and then your textbook will say use a different number. Let me get that up there, and that's another value you should put up, write down. Okay, so the critical Reynolds number for flat plate flow can be approximated as 500,000. Of course, it can vary somewhat. All right, well, that leads to the question then, in a case like this example right here, where again, this is this roof, how far are we going to go down where this flow from the beginning of the plate to where the flow stops being layered and smooth and starts being turbulent. And turbulent flow, of course, makes a huge difference in things like shear. Well, let's go ahead and do that. So that'll be part B. Let me get it up there. Symbolically, we're asking you to figure out the critical X. We're asking you to figure out X for this flow where the where the Reynolds number becomes 500,000. A note on this Reynolds number expression, you might say, hey, as we go down the plate, don't we change this U? But this U stands for the free stream velocity, the speed out here, or the speed up here, or the speed way down here where the flow is unaffected. So for this entire example, you're going to use U is equal to 22 feet per second. And let's see how big we get relative to 2 feet for the critical X value that leads to turbulence. All right, so I got 3.57 feet or 3.6 feet. Here's a little bit of the math behind it. Basically, I knew that this U X R over V, that's the Reynolds number, is have to be equal to 500,000. So I just went ahead and did my math, and I got the critical number is going to be the Reynolds number times the kinematic viscosity divided by the free stream fluid speed. If you look at the units, it works out well. I get 3.57 feet. And so what that means is if we take a look at this roof over here like this, there's a very short region where the flow actually is laminar. And then for the most part, for the rest of the roof, the flow is going to be turbulent. And that's important for things like shear analysis and figuring out what's going on. All right, that is our first calculation for the boundary layer over a flat plate, Reynolds number calculations. All right, 2 more equations for today and a little bit of practice. So some other things that we're interested in figuring out. We're interested in figuring out the boundary layer thickness. I'll talk about reasons why a little bit, but this really amazes me is that some really bright people understand math and physics just use our basic equations, F equals ma, conservation of energy, to figure out what this boundary layer thickness was, and also an equation for the shear that works in the laminar case. So I really encourage you to write that down. These 2 equations that we have right here work for the section of the plate where the flow is laminar. Okay, so the boundary layer thickness is given by 5x, okay, times the square root of the kinematic velocity, 5 times the square root of the kinematic viscosity times how far we are down the plate, x, divided by the free stream velocity, that's a u. That is equivalent to this expression right here, 5x over the square root of the Reynolds number. I believe that you're going to use this formula for your problem solving almost exclusively, but you should write down them. Okay, so there is equation number 1. I'm going to box it. Hopefully that you are denoting to yourself in your equation summaries that is for flat plate flow and that is for the laminar portion of the plate. In addition, in a theoretical fashion, they came up with an idea what the velocity profile looks like. At the plate surface, it's 0. Up here, it's actually full speed, and you end up getting a velocity profile that looks something like this, where we have slow speed. I'll get my hand out of the way in just a second, faster speed and faster speed. They came up with an equation for that velocity profile, which is, again, pretty mind-boggling to me. But then what you can actually do then is you can use that velocity profile equation to get the wall shear by taking the rate of change of the velocity with the verticality at the surface. And that led to the following wall shear formula. The shear at the surface, okay, kind of like a wall, but at a surface, is 0.332, free stream velocity to the 1/2. Then you take the square root of the density, the dynamic viscosity, and how far divided by how far we are down the plate. So that's our second equation. All right. So I think a little bit of practice is in order on that. You've got those down. I'm going to get a chart. We'll get started on that chart, and then I'll give you the answers. All right, on this example, we're going to fill out a chart, and there's going to be 3 more rows here like this. So I want you, at least 2 more rows beyond this, probably 3. So I want you to give yourself a little bit more space. And our the values at which we're going to do calculations are 1, 2, 3, 4, and 5. Okay. Strictly speaking, I should have a 0 in here. I'll talk about that. All right. So our example, we've got a flat plate. Okay. And we have some fluid approaching that plate. All right. I have made the numbers ridiculous just so, or the speed ridiculous, so that we can see how the numbers work. So I'm going to make this engine oil. Hey, I wanted to come up with an example where it becomes turbulent somewhere down the plate. And you guys know that engine oil is really hard to get turbulent. That's why I have it going this fast. Okay, we'll work out the numbers and see what it works out. So by engine oil, I mean the oil that's in the standard table at the standard temperature, SAE 30 oil. What I would like you to do is go for it. Let's just all start by getting this number and see if we can agree what it turns out to be. What is the Reynolds number 1 foot from the surface, from the beginning point or the initial? All right, you should have gotten a large Reynolds number. So a couple ways, formulas to do it. I did this formula here like this, but being a little bit more detailed, you don't have to do this at all. I worked out the kinematic viscosity by doing the dynamic viscosity divided by the density. And so I got 4.52 times 10 to the negative third. You may have just used the 4.5 number from the book. Hey, are our units working out? Feet squared per second. Numerator feet squared per second. It's unitless. And if you do it this way, you get really close to 125,000. And I actually worked out, I did these detailed decimals so that if you use the kinematic viscosity I had down here, it worked out to be 125,000. So I encourage you, if you filled in a different number, to go ahead and make it 125,000. Sorry, my writing's not super clear there. All right. Why don't you go ahead and pause and see if you can think your way through it. Is there some slick way you could get the 2, 3, and 4, and 5 without a lot of calculator work? So hopefully you've thought about it and thought, well, taking a look at this formula, as I move down the plate, the free stream velocity does not change. That's the unaffected velocity, or the velocity upstream of the plate. The fluid properties aren't changing. Its kinematic viscosity is not changing. All is changing is x. So in going from 1 to 2, x doubles. So this one right here is going to be 250,000. Okay, and then at 3, it's going to be 375,000. And then at 4, it's going to be 400,000. Okay, and at 5, it's going to be 525,000. Okay, so we have a case here where the flow actually, if we were to put markers on here, so here's 1, here's 2, here's 3, here's 4, and here's 5, okay, the flow is actually laminar for most of the plate. And of course, in general, engine oil would always be laminar for over the course of the plate. So this is an unusually high speed. But in any case, we get laminar in this first region here and turbulent over at the end. We're undergoing some sort of transition. By the way, I'm sorry, my math was poor here. This should be 500,000, and then this should be 625,000. Sorry about those numbers, 500,000, 625,000. Okay, good. All right. The next thing we're interested in doing is getting the boundary layer thickness. So why don't you go ahead and pause the video, and once again, work out the boundary layer thickness for x equals 1. All right, I got a very, very small boundary layer thickness, okay? And here's the math. There are 2 different boundary layer thickness formulas. Since we always have the Reynolds number calculated, the 5x over the square root of Reynolds number is the most convenient one to do, and I got 0.01414. Okay, I didn't think about units on that. Reynolds number is dimensionless. 5x, x is in feet, so this is going to be in feet. So our first answer that we would put in there would be 0.01414. I'm just going to do the 0.014. Okay, well, obviously that's a little bit hard to comprehend. And you'll notice this when you do flat plate boundary layer thicknesses, that initially at the plate, the boundary layer is going to be so thin that oftentimes we want to convert it into inches, or if we're in metric, into something like millimeters or centimeters. So what I would like you to do, encourage you to do, is at least write down the numbers that I have, or even work out the remaining 9 blanks for practice to get to the point where you're really good at this. I'll get the numbers up there in just a second. Hey, actually, it's less work than I initially indicated. So I took that 0.014 and converted it to inches, and I got 0.17. This one worked out nicely, so we're at about a 1/4 inch. So just a little bit above the plate surface, the flow is just that ordinary engine oil flow. The region that gets affected above the plate is very, very small initially. And the numbers show that it's growing. As we get to 3 feet down the plate, I have 0.29 inches, so it's getting a little bit larger. All right. My mistake that I said earlier was I actually said, hey, let's work it out all the way down the plate. But as we get up here at 500,000, we're entering the turbulent region, and our formula doesn't work for the turbulent region. So we wouldn't need to do these here. The formulas are in the book. Let's go spend a little time thinking about this weekend and see if we do the turbulent or what else we do to finish off the material for test 2 with our last lecture before test 2 on Tuesday. All right, well, to finish things off, let's use our last formula and figure out in this region over here, what actually is the wall shear like? By the way, one thing that would have been good for me to do is to actually have a 0 column and think about a couple of those things. So if you did the 0 column and you got the Reynolds number, you would actually get a Reynolds number as 0. And that basically means we're right at the leading edge and we're not over that plate yet. So there's really no turbulence tendency, not until we get further on. At least that's the way you can interpret it. Okay, wall shear, or basically shear at the body surface. Well, you got your formula, so let's see if we can get this number right, and then we'll wrap it up. All right, mathematically not a challenge, but unit not that bad. So I ended up getting 531 when I plugged into my basic formula. That's the wall shear or surface shear formula right there, 0.332, free speed velocity raised to the 3/2, and then we've got the density, we've got the dynamic viscosity divided by how far we down the plate to the 1/2. So there's 531. So what I'm going to fill in there is I'm going to fill 531 into that. And let's confirm that the units are as they should be, and that is a challenge. So I'm going to get at it pretty quickly, but ask you guys to maybe think about it yourself or once the lecture is done. So I just started by taking a look at this whole big bracket here like this. What's going on with that bracket? So ignore the 531. We're over here like this, taking a look at that bracket. So I've got a slug per foot cubed, okay? I've got a pound-second per foot squared because of the viscosity of a foot. So if I congregate all that stuff, okay, into a single unit, I get a slug, I get a pound, I get a second, and wow, I get a foot to the 6th. Okay, in short, one way of thinking about this is we would like to take that slug and make it into a pound. So I took that slug and added a foot per second squared, and that makes that into a pound. Well, if I add a foot per second squared, if I had a foot in the numerator, I'd have to add a foot in the denominator. So that makes that denominator from feet to the 6th to feet to the 7th. And if I add a second squared in the denominator, I add a second squared in the numerator, so that's second cubed. All right, so then it's really not quite that bad. Okay, that was a pound there. So now I have pound squared, second to the 3rd. Sorry about my holding this here. I'm getting kind of near the end. And foot to the 7th. So what do I do then? I end up taking the square root of all that. So that's pretty nice for pounds. That just becomes pounds. Okay, and this becomes seconds to the 3/2. And the denominator becomes feet to the 7/2. Well, if you combine what we get over here from this square root term, we've got a foot to the 3/2, okay? And we have a second to the 3/2 in the denominator. Well, this second to the 3/2 cancels that second to the 3/2, and that ends up being gone, okay? And then feet to the 7/2, feet to the 3/2 ends up being feet to the 4/2 in the denominator, and that's feet squared. So our units end up being pounds. Let me write that down. Pounds per foot squared, which is what we want for shear, pounds per foot squared. And thinking about that, what that means that this oil is creating at this point right here, is creating 531 pounds of shear that way, of drag essentially per foot squared of surface. 531 pounds, that may seem incredible. Once again, this is engine oil. Engine oil is high viscosity stuff. So if you thought, hey, I'm gonna drag this plate through this engine oil at that speed, well, of course, there's gonna be a lot of backwards force. That's where that 531 comes from. Okay, I'm gonna give you the rest of the values and then we'll wrap things up. Okay, those are the other two values we can figure out. A shear of 375 pound per foot squared, 2 feet down from the leading edge of the plate, and 306 pound per foot squared as you get 3 feet down from the leading edge. We can't figure out these two because right now we haven't evaluated whether our shear formula works in the case where the flow is turbulent, okay? All right, well, that's good enough for today, you guys. I have a lot of work to do in order to keep us going on. Let me just mention very briefly, I like the idea of us all taking test 2 at the same time. Test 2 is going to be at the end of the week. I'm going to propose a couple times. I ask that you consider it strongly, taking those times and not dismiss them out of hand. There's a lot of advantages for a little bit of a delayed time, maybe like a Thursday evening or Friday. In particular, you're going to have more time to study and I'm going to have more time to answer questions. More about that later. Right now, why don't we take a break? We've worked pretty hard for a bit.